if we could take a look at problem number 30. It says to determine on which intervals that f is concave upward. Now, remember that our first derivative, the intervals where the first derivative are positive is increasing, negative is decreasing. The intervals of concavity, upward positive and downward negative, is for the second derivative. So if we look at problem 30, the first step you want to take is to find the first derivative. So if we drop the power down front, multiply by 1/10, 5 times 1/10 is 1/2. Power goes down by 1. 4 times 1/6 is 2/3. Power goes down by 1. 4 times 3 is 12. Power goes down by 1. And then we've got 87, and then the 69 derivative is 0. Okay, now that's our first derivative. The first derivative doesn't give us any information about concavity. So we're going to have to do it again. So there's our first derivative. Now let's take our second derivative. So we're going to use the same tactic because all of these are individual power rules. So 4 times 1/2 is 2. That would become an x cubed. 2/3 times 3 is 2. That's going to become an x squared. 12 times 2 is 24. That's going to become an x. The derivative of a constant 87 is nothing. So in order for us to answer the question, we need the critical numbers of the second derivative. So we're going to set this equal to 0. And then after we do that, we'll put the critical numbers into a plus and minus chart. So you do the same thing to the second derivative that you would do to the first derivative for increasing and decreasing. We find the critical numbers, we make a plus minus chart, Now all of those things are divisible by 2 and also contain an x. So always look for that greatest common factor if you are doing any type of factoring. If we factor out the greatest common factor, we're going to be left with x squared plus x minus 12. Now x squared plus x minus 12 is a factorable quantity. If not, you can always find those particular critical numbers by using the quadratic formula if you have the urge. But I'm not going to. I know it's factorable to be x plus 4 and x minus 3. Now, from there, let's think about our critical numbers. Our critical numbers occur at 0, -4, and +3. Remember, they always switch signs. You can set each one equal to 0 and actually physically show that if you have the urge to do that. Now, I'm going to put that on to a plus and minus chart in least to greatest number line order. All of those are critical numbers that exist, so I'm going to put dots there. If they didn't exist in the original function, I would put an open circle. And I have to list all my factors to the left or right, it doesn't matter. I'm going to put 2x here, x plus 4, and x minus 3. Now remember how we do that. We need our test values within the region of the number line. So let's just go -5, -1, +1, and 4. Now, let's plug -5 into all 3 of our factors, and let's just write whether we get a positive or negative. We get a negative, a negative, and a negative. Now, 3 negatives are multiplied or divided are going to result in a negative answer. Let's plug in -1. We get a negative, we get a positive, we get a negative. 2 negatives now are going to multiply it together and give me a positive value. Now let's plug in 1 to each of those and determine what our sign is there. If we plug 1 into each of those, we get a positive and a positive and a negative. 1 negative multiplies and gives us a negative. And then if we plug in 4 to all of them, we get positives down the board. All positives are going to remain a positive. Now let's summarize our answer. Now they asked us about concave up, I believe. Yes, concave upward. But I'm going to write it out so that you kind of get a sense of what's happening here. So it is concave up everywhere that the second derivative is positive. So that is from -4 to 0. Increasing, decreasing, concave up and down, we don't include the endpoints. It's not going to be a big deal otherwise, but, you know. And then we also have a positive section from 3 to infinity. Now, that's the answer they were looking for. They were looking for this section and this section. But let's summarize everything else. So it is concave down from -infinity to -4 and also from 0 to 3. We have a change in concavity. A lot of functions don't have a change in concavity in this many places, but we have an inflection point when x equals -4, 0, and 3. All three of those values happen to be inflection points, which that's not super common that happens. Okay? So that is one where you had to find the first or second derivative and go from there. Now, do we have any questions about number 30? Yes.
How do you find an inflection point again?
An inflection point is always on the second derivative chart, on your concavity chart, if we have a switch from negative to positive or positive to negative.
Okay.
So -4 is an inflection point,
Okay.
0 is an inflection point, and then 3 is an inflection point. They all had that switch over.
Yeah.
What can happen sometimes is you'll have a negative, then a negative, and so that wouldn't be. And so this, in case they're all inflection points. Okay, now, I did give you one like 31 on the test where I have given you the derivatives, and then you have to create the chart from there. So you don't have to do the derivative work, but you do have to do stuff related to the charts. So in 31, it says, determine the intervals on which the function is concave down. Now, let me just remind you, if I said, where is the function increasing, or where is the function decreasing, which derivative do we use? If I say, where's the function increasing, or where is the function decreasing, we use the first derivative. But if I say, where is the function concave down, what do I use there? Second derivative. So let's focus on that second derivative, okay? They have been kind to us. They've given us the second derivative, so we can immediately jump to the point of let's find the critical numbers. There is a critical number where the top equals 0, so 0. There is a critical number where the bottom equals 0. The cube root of 0 is 0, so you don't have to include the power. We'll have to include the power in the chart. We won't include the power otherwise. That is a factorable quantity, or if you do the square root, you would get a plus or minus. So however you slice it there, we have positive and -2. So we're going to put on our number line 3 values, -2, 0, and 2 in number line order. Now, the values from the top are points that actually work. So this one is a point. So let's make it visible as a point. These two are undefined values. Most likely they are undefined all the way back to the original function, because as we take that derivative, like the original might just have x squared minus 4, and then the next one might have a squared, and the next one might have a cubed, and the next, you know, so mark those as those are not points that are included. Okay. Now, let's put our factors to the side. I'm going to leave them just top and bottom. It'll just simplify things a little bit. We're going to use test values. Let's go -3, -1, 1, and 3. If I plug -3 into both of those, I get -18 or a negative on top. On the bottom, I get 9 minus 4 or 5 cubed, which is a positive. A negative and a positive make a negative value, whether they're multiplied or divided. If I plug in -1, I get negative. I get 1 minus 4, which is -3. If you cube a negative, you're going to keep it negative. 2 negatives make a positive. If I plug in 1, I get a positive. 1 minus 4 is negative 3. If I cube it, I'm still going to get a negative. If I plug in 3, I get a positive. I get 9 minus 4, which is a positive. Cube it, I'm still going to get a positive. This one would be negative. This one would be positive. Now, they asked for the intervals on which it is concave down. I'm going to give you the intervals everywhere. You know, we'll do all of it. It is concave up on our positive pieces from negative 2 to 0, and also from 2 to infinity. It is concave down on our negative intervals from negative infinity to negative 2, and then also again from 0 to 2. Although they didn't ask it, I want to summarize everything because, you know, on the test I could ask you whatever. There is an inflection point at x equals 0. Now, the reason I wanted to look at this example, because although this seems to be a change in concavity, does that point exist? So can it be an inflection point? No. So there's probably a vertical asymptote at that point, and so we would not include that. Same thing happens here at 2. That point doesn't exist. It can't be an inflection point. How can you have a point where a point doesn't exist? The only point that it would be included would be at 0. There is an inflection point at 0. Most likely, there's kind of probably like a little cubic between two asymptotes if you were to graph the original function. Okay, so that is 31. I'm looking. So we have done a lot with our derivatives. And there's still a few more things we got to do. Let's talk about asymptotes for a minute, because I did mention vertical asymptotes. There is some questions about asymptotes on the test. Could we go up to problem number 10, please? Number 10 says to identify all the asymptotes of the following. So let me give you some rules that you can follow for asymptotes. A vertical asymptote is where the denominator equals 0. Unless it's a whole occurs when you have a factor in top and bottom that equals 0. And then a horizontal asymptote, you have to compare the powers. So we'll talk about those as we go, okay? So vertical asymptotes is where the denominator equals 0 unless that's a whole, because both the top and the bottom values would equal 0. Horizontal asymptotes, we're going to compare the powers. We'll talk about those in a second. Okay? Okay. So let's start with A. It is in factored form. That's a good way to start. We can't break it down further. The top factor, x minus 2, equals 0 at 2. That is an x-intercept. It's good. It's a great point. But x minus 1 is the problem. X minus 1 equals 0 is a vertical asymptote. It doesn't have a matching factor in the top, so it's its own thing. And so we have a vertical asymptote at 1. That's the only undefined value of this particular function. There's no holes, there's nothing else. It just has a horizontal or a vertical asymptote at 1. Now let's talk about end behavior horizontal asymptotes. The horizontal asymptote is determined by the powers, the highest power term on top and bottom. Use the coefficients since they match. So an x over an x, we're just going to use y equals 1 over 1, or 1 is our horizontal asymptote, or that's our limits to infinity. So both sides of these function, going to positive infinity and negative infinity, are heading to a value of 1. And that's all the way back from the beginning of the year. That's a kind of a pre-calc thing we had done in the past. Okay. Let's take a look. Since C, we're right under here, let's just do C. There's only one factor in the bottom, x. It doesn't have a match on top. So x equals 0 is your vertical asymptote for that one. Horizontal asymptote, throw this out. Just focus on that. So what is the square root of x squared? X. So the highest power on top is just an x. The highest power on the bottom is just an x. So we do just get to use the coefficients on that. So it is a horizontal asymptote at 1 again. Okay. So horizontal asymptotes, you always look at the highest power thing. The highest power thing is the square root of x squared. The square root of x squared is x. So the top, if you throw in very, very large numbers, adding 4 does nothing. So you just keep starting to act more and more like an x. So you'll head closer and closer to 1. Now let's look at b. The problem I'm having with b is that it is not in factored form. So I need to factor that. That's x minus 2 times x minus 1. Just follow unfoiling rules, factor that. And then the top factors, but so does the bottom. That is x minus 2 times x plus 2. Now, the sections of factors that match on top and bottom, there is a hole at x minus 2 equals 0 or at 2. That is not an asymptote. There's a hole in the graph. There's just one point you jump over. There's a little hole in the graph. But the remaining factor of our denominator is going to cause a vertical asymptote. So you have to set that equal to 0. We get negative 2. Horizontal asymptote, we can use the simplified version or the unsimplified version. The highest power is x squared. When they match, we just get to use the coefficients. We see a pattern here that horizontal asymptote is 1. Let me remind you, if we had a function that looked like x over x squared plus 1, if the higher power is in the bottom, the horizontal asymptote is always 0. If the higher power is in the bottom, the horizontal asymptote is always 0. Okay. The problem I'm having with D, again, is the fact it is not in factored form. So let's take a look at getting that in factored form. So that's x plus 3, x minus 3. This is x minus 2 and x minus 3. What factors are causing a hole in the graph? The x minus 3. So there is a hole where x equals 3. Now throwing that out, the remaining factor that is in our denominator will cause a vertical asymptote. So where is a vertical asymptote for this one? When x equals 2. What's our horizontal asymptote again for this? Yeah, the powers on top, powers on bottom match. You use the coefficients. 1 over 1 is 1. There you go. What's the difference? Okay, so if we had something like 2x squared plus 1 over x squared minus 3, what's the horizontal asymptote for that one? What's the horizontal asymptote for this one? It's going to be 2 over 1. So watch those coefficients. It is always the coefficient on the matching lead term. It's always the coefficient on the matching lead term if the powers match. Okay? So that is a little bit about asymptotes. Now, I need to do one where we talk about the slopes of the tangent. Okay, so let's now do 16 and 17. So I'm assuming today we're going to finish everything related to derivatives. And integral should be the thing that's most recent in your brain, so hopefully it will be the most, that you'll understand and remember. But anyway, let's take a look at 16 and 17. I want to add a page here so that I can have somewhere to write. Okay, so 16 and 17 is up next. Let me take a little screenshot here. Okay. Okay, so let's start with 16. It says, find an equation of a tangent line to the curve when x equals 2. Okay. Now, you might recall, I think this is one we actually got to finish the vocab. The first thing you want to do is find the first derivative. Second thing you want to do is you want to plug in the value, and so you want to find the slope of the tangent. The third thing you want to do is y minus y1 equals m times x minus x1. Okay? Okay, so we're going to follow those 3 steps for both 16 and 17. 16 says, find an equation of the tangent line to the curve defined by y equals 2x squared minus 5x plus 8 when x is 2. So the first step we take is we find the first derivative. So our derivative is 4x minus 5. Second step, we need the actual slope of the tangent. You find that by plugging in whatever value you're looking for into the first derivative, because that's what the first derivative tells us, the slope of the tangent. So if we plug in 2, we get 8 minus 5, or 3. Now, for step 3, we have to plug a point and a slope into y minus y1 equals m times x minus x1. Now, we already know the slope is 3. We know the x value is 2, but don't be fooled. We actually have a little bit of work to do. If you plug in 2, you get 8 minus 10 plus 8, which is 6. So we do need a full point there. Sometimes they'll give you the point. They'll say, at the point 2, 6. But sometimes if they only give you the x value, you know how to find a point. Just plug in. Back to the original, to the original, to the original. Okay. So our equation of our tangent line is y minus 6 equals 3 times x minus 2. Now, I'm not going to show you how to rearrange that. I hope you know how to do that. If you need to solve for y, distribute it in the 3, add 6 to both sides. Now, let's jump to 17. It says, at what point is the tangent line to the curve parallel to the line y equals 3x minus 7? 2 lines are parallel if their slopes are equal. So we're really looking for, when is the slope of the tangent going to be the same as the line 3x minus 7? What is the slope of the line y equals 3x minus 7? 3. Just pull the 3, take the coefficient off of your x. So we are looking really, where will the slope of the tangent equal 3? That's it. Okay. So how do we find the slope of the tangent? The slope of the tangent is related to our first derivative. So we have the same exact problem from before. We found the first derivative was 4x minus 5. So we're really just saying, where is 4x minus 5 going to equal 3? So it's a very nice problem after that. Add 5 to both sides, divide by 4. Now it says at what point? Well, they just so happened to give us that 2, 6 again. So 16 and 17 actually kind of end up with similar answers. They're completely related. Okay, makes sense for that. Now, the last type of derivative stuff are some optimization problems. Did I put a related rate on here?
Those make me mad.
Just plug, anytime you want a point that touches your graph, just plug the x value back into your original. I plugged the x value right into there.
So 2 back in.
Yeah, 2 back. So it'd be 8 minus 10 plus 8.
Okay.
I do not have a related rate problem on there that I see. I believe I might put on one for bonus. There isn't one yet. But there is an optimization problem. So let me find where the optimization one is. There is one in this review packet
If
somewhere.
I do better than the curve, does that mean I get bonus?
No, you would set the curve. Okay.
Oh, so if we all just fail.
Don't. Okay.
Did you put a curve on the last test?
No.
Really?
Mm-mm.
Oh, that's great.
Oh, let's do 39.
See, we thought we all did worse than.
I
Pretty good on
was
it.
very nice when I graded. How about that? There wasn't a curve, but Mrs. Hott was very forgiving.
Are you gonna give those back to us?
Oh, yeah, I've got them. Okay. Okay, let's look at 39.
She said, oh yeah. She said 39? Why is 39 so squished in there?
I have no idea. That's why I needed to make some room. Okay, let's look at 39. It says, what is the maximum area of which can be enclosed by 200 feet of fencing if the enclosure is in the shape of a rectangle and one side requires no fencing? So the way that I do this, I always will draw the shape and assume this side might be up against a barn. This side might be up against a river. There's something there that they don't need fencing on that side. So we really just need 2 X's and 1 Y. So we know that the fencing, we'll call it perimeter. Well, let's call it fencing. Is 2 X's plus Y and can total 200. Okay, so that's the first thing. What do we know about this? And we want to find the thing that that we are trying to maximize. The area formula for a rectangle is length times width. In this particular case, that would be XY. So we have 2 things. We know that 2x plus y has to total up 100, and we know that our area is xy. Now, when we did maximization problems, a maximum occurs where we look at the first derivative and we see that it goes increasing to decreasing. So we're kind of just doing a first derivative problem once we set it up. The problem is we have 2 variables. So the first thing you want to do is do a little rewrite. Find in the equation that relates how much fencing you have, how much whatever you got, how much cardboard you have, whatever. You want to solve for the easiest variable. So y is just kind of sitting there. So let's subtract 2 x's from both sides. And that's where we're going to put into our area equation because we only want 1 variable. Just like when we did related rates, you always, at this point, before you do the derivative, need of 1 variable. So that's going to be x times 200 minus 2x, or 200x minus 2x squared. Now think about it for a minute. You don't need calculus to do this problem. The formula is an upside-down parabola. The maximum always occurs at the vertex. So technically, because it's a simple problem, we could find the vertex and go from there. But I'm going to pretend I don't know that, and I'm going to do it using calculus. So a maximum requires a plus or minus chart for our first derivative. So you just take the first derivative. So it's just going to be 200 minus 4x. Doesn't a parabola only have 1 critical point, the vertex? So the first derivative is going to give us that vertex. And so if you do 200 minus 4x, and you set that equal to 0, that's going to be the critical numbers of the first derivative. We get 200 equals 4x, or x equals 50. Okay, now that's what x is. Always read the problem. If they say, what is the maximum area, we need x and y so we can multiply them together and find the area. If they say, what are the dimensions, what's the y dimension? Well, the y dimension is 200 minus 2 x's, or 100. So if they ask in the question, what dimensions will give us the maximum area, you would say that the width would need to be 50 and the length would need to be 100. If they said, what is your maximum area? Remember, area is just length times width, so it's just 100 times 50, or 500 square feet. Okay? So,
No,
It's 5,000.
5,000.
oh, 3 zeros. How about 3 zeros?
That's why I said no.
I was like, what did I do? Okay. So it's 5,000 square feet would be the area enclosed by our fencing. Okay? So that is a maximization problem. Yeah.
Couldn't you just get 200 and then just get 100 and then divide that by 2 for the two sides? You got 50 on each side.
Yes and no. Be careful. It doesn't always work out perfectly like that. It depends upon I mean, some of these can be done logically. Like I said, even it's a vertex. We know how to negative b over 2a. I mean, there's multiple ways to do these problems. Logic is one of the ways you can do it. Okay, now let's do an optimization. Not an optimization, I'm sorry, related rates. I just got to.
Just do the bottom one.
Well, the bottom one. You mean 72?
Yeah, just because then I don't have to copy it.
No, that is not something we can do. We did not get to work. That's a physics thing. We haven't done
I don't like physics.
that.
Physics is yucky.
Scrap the review.
It was so fun.
Okay, let's do 44. Let's do 44.
44. That means I gotta go back and copy it.
Right. That's what I'm saying. That's why I said we should do the bottom one.
No. The bottom one's ooky, and we just aren't ready for it.
I don't want to do it for you.
I don't want to do physics.
Yeah. Let's do 44.
Hold up.
Okay, so I just added a page for any of you that are trying to do that. Okay, it says a train leaves the station traveling north at a rate of 60 miles per hour. So we're going to make like a little XY axis sort of thing. Let's label it north, south, east, and west. Okay.
So a compass?
Uh-huh. And
We're good at compasses.
The what?
We're good at compasses. Compasses.
Can we label north by compasses?
no. Okay, so now it says we are traveling north. We're going to call that y. So dy dt is 60. Well, I just needed that for my brain, actually.
Well,
I need a little compass.
I don't know how to
I'm just labeling my axes.
Why aren't you
north, south, east,
moving?
and west.
Come on. Okay. Whatever. Oh, you do
Draw
that.
a circle around it.
Okay. It says 1 hour later, a second train
Oh my god.
is traveling at a rate of 45 miles per hour. Find the rate at which the trains are separating 2 hours after the second train leaves the station. Okay. So they're separating, we're looking for this. We're going to label that C. Okay. Let's think about what we know. If we look at our triangle for a moment. Gosh, I'm so good at this. The second train only went 2 hours at 45 miles per hour. It would have gone 90 miles. Distance equals rate times time. But the first train actually traveled 3 hours because it left an hour early. And so if it's going 60 miles per hour, it's actually going 180 miles. Okay? Now, using what we know about the Pythagorean theorem. If we do 180 squared plus 90 squared, you get 4,000 or 40,500. So that's the square root of 40,500. That is divisible by 8,100 maybe? 4,500 divided by 8,100. Yeah, and so that is going to be 90 radical 5. Just trust me. Okay.
Okay, then.
All right, Mrs. Hall.
Yeah, okay, anyway. Now, what relationship do we have about how x, y, and z are related? We know that x squared plus y squared equals z squared. I left it x, y, and z, so yeah, because I'm going x direction, y direction. Yeah, that's the way I normally do it. Yeah. Okay. So this is differentiation with respect to time. So this will be 2x dx dt plus 2y dy dt equals 2z dz dt. Okay. Now, let's fill in everything we know. X is 90. Dx dt was 45. Y was 180. Dy dt was 60. Z was 90 radical 5. And I don't know dz dt, but that's what I'm finding. Okay. Let me get the left side into one thing. 2 times 90 times 45 plus 2 times 180 times 60 is 29,700. And that's 180 radical 5. Now we need to get that dz dt by itself. So we have to divide both sides by 180 radical 5. Now 180 does go in perfectly into that 29,700 figure, so you actually get 165 over radical 5. Now let's talk about 165 over radical 5 and how to make it nicer. You should rationalize it. If you pop a radical 5 to the top, it would leave a normal 5 behind, but 165 is divisible by 5. So your answer is 33 radical 5 miles per hour. So that's a related rates problem. So we are going to stop here. Please return this in immediately. Tomorrow we're going to talk about some integration stuff. We'll practice anything related to integration that will be on the test. Please be studying every night. You should be doing calculus every single night. You should be reviewing this stuff. This will not be an easy test. So tomorrow we'll review integration. There you go.